Hello, people. I am going to go through some of the last little bit here, and I think I will be just about done with the pieces. Excuse me. So here, as I mentioned in my previous Collatz video, if you take the expressions, right, you take the 6x plus 3 and you go to the two columns that can contain powers 2, you have a minus 1 and a plus 1, right? 3 times an odd plus 1, 3 times an odd minus 1. You set both of those equal to the even, and you can find the loops. So in this particular one, in the negative, and I'm going to start here, and it's illustrative, so bear with me. If everyone's waiting for me to get to that, I will. I'm sure there's all 4 people that watch this video. But everyone who does is probably the important ones. So anyhow, so yeah, you get this 3 times n, right? We'll just say n is this number. It's going to be odd. Minus 1 is equal to 2x. And you get this. So you get like 3 halves 5 minus a half equals 7. Right? So anytime basically, essentially, if 5 were to go in here, you would get 7 as the output. And then you go to the next part of it where you have to have the other condition that's satisfied. And that's where 3 times this x prime minus 1 is equal to some power of 2 times that same n. Right? So you put 5 in here, you get 7. You put 7 in here, you get 2 squared times 5. Right? You get 4 times 5. 3 times 7 minus 1 is 4 times 5. So anything that would fulfill this for some value a that fulfills those 2 conditions would loop. And same would be true for that one, and I'll get to that in just a second. But the next point I'm going to make is that for this whatever this value is for any given n and x prime, right? For whatever value this is these values are going to be 1 integer higher, right? For n equals 1, you get 3 halves minus a half equals 1. For n equals, right, 1 over here, you get 3 halves plus a half equals 2. There's a single integer difference between these 2 numbers, right? For the same value n, regardless of what n is, as long as this n and this n are the same, this one will be 1 less than this. We've already established that these are this is an odd, which makes this even. This is 5 and 7, this is 6 and 8. And it doesn't take much to look up here and realize what these are, right? You get whatever you put in odds, you get something out. You'll get an odd loop out. Here, you put in odds, you'll get an even loop out. It's not every value is going to loop, but any value that loops will be of this form. And same here. And these will be even, which means that they'll continue to divide by 2. It'll continue to run down. This one right here can loop on odds. So those are the only 2 possibilities. This one will loop on evens. This one will loop on odds. And that takes care of the loops. In the previous video, I talked about the runaway odd and the supplemental to it for anyone who looked at the 5, the trivial answer. And then this should prove all values for loops, and it shows that this one will loop on even, so you'll never encounter a loop because it will always divide by 2 and go to a different odd. It will only loop on even values for n and x prime. And then that should take care of all the pieces for the Collatz conjecture, and as I figure out how to put it together into all the little plot pieces into a coherent story, I can put that into a paper, submit it to the American Mathematical Society, and see if I really just did it for reals, which I don't know enough to know why I don't, and I can't find anyone else who does either. I think that means I'm right, but we'll see. The world will tell me. There's no one else who can. So there's the rest of my Collatz conjecture, everybody, and I'm going to put it together in a paper and submit it. It's the same thing I wrote months ago, expanded. Never changed, never wavered. Anyway, that's it. This is a dosager on the Collatz. I am said person. Signing off. You guys have a great night.